Hello everyone, welcome back to Remaking with Stewie. In this session, the goal is to see how can we read a binary file in Python and try to understand like hexadecimal and decimal uh, type and all of that. We will look into bytes in Python. And the goal at some point is to, and remember, is we want to extract the text coming from these pointers, so this pointer table. So first step is to extract each pointer, and from there we will be able to know where the text is localized. So we need to open this SLPS file. So if you remember my folder architecture, we have created in the last session this SFRWA3 folder, tools, Python. So our class is here with our main code. I've created a new file, whip binary. The whip is work in progress because it's more like to test the code as we go, and then we will create a function maybe at some point. So I just created a new file like this, Python file whip binary, and I will create a configuration based on this one. Let's call it test binary file. And our code will be, script will be whip underscore binary, no parameter, no need, and this should be okay. So first, we will need to store the path of our SLPS file, so our binary file we want to read. If we are here, we need to go 1, 2, 3 level before we go on the original folder where we have the ISO file. So we can go 3 level I like this, and then go in the original folder and find the SLPS file like this. We need to use these double dots because the working directory from my configuration, as you remember, is Python. It would be a different story if, let's say, you would have put this instead and like take this section and put it up above. It can work. At some point, I might want to change, but for now, let's stay like this. It's not a big problem. So this is a string storing our path, our relative path. And from there, we can open the file that is at this path. When we open a file, we can use the R type. You need to decide you want to open this file only for read operation, read and write, or write operation. And you also need to specify if you want to open it as a binary file or as a text file. So if you want to open with the binary file, you'll need to use the RB type. And from there, I can create a variable as f. So I will have a stream that will be f for file. And with that stream, I have access to other operation. And it will only live inside this with statement. I will have this. So maybe I can stay zoomed just to help you. There's probably another way of zooming in this. No, I'm not sure exactly. How do you zoom in? Eh, let's see. How does it look? Yeah, I'll stay zoomed for you. So by default, the stream starts as at the first position in our binary file. So it will open the file here, so SLPS, and it will be here, the first byte, position 0. So I can do a f read operation and say read the first byte. If I do that, I can store it in a variable like this. Maybe, and I'll just put t equal to just to debug. Let's put a breakpoint and go into our debugger like this. We see that inside B we have \x 7f. So this is a format for binary. So binary will always start with B apostrophe \x 7f, and this is our 7f that we have here. If I want to read 2, it will read the it will read 2 bytes at the position that we are. So we are still at the first position right now. 7f, and you see E uppercase. It's not giving us 45, it's giving us the E that is here. So by default, the Python try to convert it to like text using ASCII encoding. So that's why sometimes it gives you weird result like this. But yeah, it's not a big issue, I think. But yeah, so if we want to read 4, you can read 4, right? And so if we can do like first, then second, and do another call, fread 4. What will happen? Let's put a breakpoint here. This read the first 4 bytes, so until the end of elf, these 4, that's what we see here. And then the other one, 0, 1, a bunch of, so it reads, so it always, the read, remember, always read from where, there's like a pointer to where the position is. And right now it's right here. If you want to know the position where you are on the file, you can use the tail function. So or we call it pos for position. And if we debug 8, 8, 0, 1, 2, 3, 4, 5, 6, 7, and 8. So it's probably not starting at 0. It's probably starting here. It will be this 8, actually. That's interesting. Let's do another read. I will stop debug. Third, read 4. Do the same thing again to 12. So something is that the f.tail gives you the decimal position. It doesn't tell you the hexadecimal position. Sometimes I feel it's easier to use the hexadecimal, so I like to do x. I call the function x, and it converts this integer, so this decimal, to a string that is in hexadecimal. So the representation in hexadecimal. So 0C, so it's not too bad. So 0C is here, so it's easier to know where you are. That's what I feel. So this is read X bytes from position, from the current position in the stream. This is tell me the position, tell me the current position in the stream. And we also have go to this position, which is f.seek. So with the f.seek, you see its offset is integer, so we need to use a decimal. Of course, we can use a decimal like this. Something that is very nice in Python, and I will show you in the Python console. So let's move to the Python console. This is very nice when you want to test different operation in Python. So if I do 0xc, it converts to 12. So it's always easier to go to a position in hexadecimal, because usually if you are inside a hexadecimal editor, you know the x position like this. It's always an x, so it's a lot easier. So go to the position hexadecimal 0c, and from there I can do a new read operation. So 0C, maybe not 0C. Let's go at 020 and let's read the four bytes here. So 020 and do a read, new read. Let's do that. We have a P, we have this and this. Yeah, because it's these characters, right? So seems to be that. So now we know how to read, which is useful, and something that you need to remember is when you read something with the regular read, you get first a byte. This is the result is a bytes format like this. We see the bytes with a B apostrophe, and it reads the bytes in a sequential order. So if you're here, what you get is exactly what you see, this sequence in the same order. But if you remember for our Python for our pointers, they are stored in little endian. So when we read, if we just use the regular read here, it won't give us the address in memory. We actually want to see 4FDE00. That's what we want to see. For that, we use the struct library in Python. So import struct. And with the struct library, so let's stop debug. So let's with the struct library, we will be able to extract the values using little endian, and I will show you in a second. So first, let's seek at the position of our pointer table. So go to our pointer table. Let's go to our pointer table. It would be this offset. And from there, we can actually test the read and see what we get from that. 0, 0, something DE, yeah, DE for F. So the 0 here is probably the 0 that we see here. You see, that's the for F in ASCII. So this is not what we want. So we can use instead, let's call it pointer value or memory address. We can use the function unpack. So unpack takes bytes. So we need to have these 4 bytes. So using the read method. So let's do that. Let's call it first bytes read 4. So this will be this sequence. And from the unpack will take care of reversing the order and give us a decimal number. That will be the address in decimal. So unpack. First is the format. I need to specify to use a little endian. So I need to use this, the symbol. This would be big endian. And then I need to use unsigned integer. So this is telling me that unpack bytes that are unpack 4 bytes. If I will need to unpack 2 bytes, I will need to use a different symbol. And I can use unpack a struct as it has a good documentation on that if you look for it. But this will be enough for us. So, and then I will specify my bytes. So if I do that, let's do this and struct.impact memory. So unpack by default give us the tuple, so like 2 object. So I basically need to force it to take the first one. You just need to remember, okay? So let's take the first one by using the bracket like this. And then memory address will be a int. So this is in decimal, remember. We can convert it to hexadecimal, maybe memory x. Let's use the hexadecimal function like this. For f, de00. Remember, this is in memory, yeah, right? But when we look at inside the game, we actually found some text here. I probably have it open. So if I go in memory, this is the text that we have, this string. When we are in Python, we actually work with the file. We don't see what we have in memory. The goal is to extract text from a file. So we need to get the position in the file. So from the memory, we said that we can use the base address that was FE100. You remember when we found some text in memory, we found the same text in the file, and then we did a subtraction between the two, and it gives us this number in the old video. So this is my base address that I will store somewhere in my code. So for now, I'll store it outside. Base SLPS equal this. So I use the same technique to use hexadecimal. So I know if I take this, if I take the position in memory and I remove this part, I will get the position in the file. So we can have a file address, another variable, which will be memory address minus our base SLPS, and these two needs to be in decimal. Remember, memory address is in decimal, and this is just a string representation in hexadecimal. This is subtraction between two decimal, and file address will be in decimal. So we could have another variable, file x, just to know, show me. Sorry, I removed something. It should be base something. Yeah, let's go debug. 3ffd00. What do we have there? 3ffd00. It's the same text that we have in here. 3, this is here. D, with B, 8B, 43, 97. And this is what we hope to see here. So with that, we can loop on all the pointers and sorry, where was it? It's here. Okay, I need to. We could loop on iterate on all of these pointers and make a list of all the offset of each entry in the file. And we will specify to stop at this position. So this will be the stop position because everything that is after doesn't seem interesting. Probably you will tell me, yeah, but we do see some things that look similar here. So like this one and these two, they actually look like pointers, but for now, we will not think about them. Yeah, there are a couple of things like here, maybe. For now, we exercises only focus on this table. So I will stop here at the last pointer, and this address is 3C, 9C53. So let's store pointer start will be a variable and pointer end 3C, 9C53. This is the end and the start. Let's see. Sorry for my French. It's easier to read numbers. So we have a start and an end for our pointer table. So we could read all the pointers starting from here until we get there, and see what we have. So something we can do is like this is a bunch of tests, so we can keep it for now. Maybe from here, instead of having this hard-coded, we can go to the start of our table, and this will be a variable that is pointer start. Let's remove this for now. Now we move to the start of our table. We want to iterate and see what do we get. So we can, there are a couple of ways to do it. Something that we can use is a while loop. So we can do a loop only when the position is lower than the pointer end. And what I will do is I will read the pointer value. This is, remember, we said it was the memory address with the struct and unpack. So let's write it like this for now. But you will see at some point that it gets a little bit crazy, and you always need to remember, okay, I need to use this I, and I need to read for. So right now I'm not using a variable, but since I start here, it will read 4 bytes and converts it into this memory address, and I need to take only the first element of the tuple. From there, I have file address that will be base plus memory. No, sorry, memory minus base. And we can have a list, could create a small list, text offsets. This is a empty list, double bracket. And we can append element to this list, text offset append. So if we go here, a list, this is empty. I can append stuff to it. And then if I print again, I have a bunch of things. I append 5. If I need to append 2 elements, I can store them in a list like this. And I can extend S. And this will add it to the n. So it added these 5 and 6 to the n. Nice. Okay. So text offset is a list. We can append the file address, which is interesting. Maybe we can also keep the, it would be interesting to keep the pointer offset. So, you know, the position of the pointer, like this is the position of the pointer here. So let's do that. We can append a tuple. The first element will be the pointer offset. So this is the position of the file. Only problem is I read already 4 bytes. So my position after I've read 4 bytes, it's not the position of my pointer. So I should probably store it first, the position, and then read to actually have the position of my pointer. So because every time you call read, it moves the cursor of the position in the stream. So if you call again f.tail, it gives you a new position. So pointer offset, and then let's call it file address. Since I'm using offset and address, I think it might be better to switch to only offset for now, from now on, just to be consistent. All right, offset, sorry. Okay, so I need to close my bracket. So this is a tuple. Can be, you can have, there are multiple ways of doing it. But yeah, but for now, let's do it like this. So we have a while loop until we get here. It should be fine. So technically, when it will do the last one, it will read here, and then the position will be here, which will be equal. So if it's equal, it won't go into this thing because there's no equal here. So we should be fine. And if we count, we expect to have, there are 4 pointers by row. So 4, 8, 9. We expect to have 9 elements. So let's debug. It will execute our while loop. Then, and what do we have inside our text offset? We have actually a list of 9 elements, where for each element we have a tuple. This is the pointer offset. This is the text offset. From there, if we need to use this thing and do something in the future, we can do a for loop and iterate on all the elements of our text offset list. So since text offset contains a tuple for each element, we can actually use uh, maybe let's call it differently, maybe just to no, we can use the same variable. It's not, it's okay. For each combination inside text offset, I can actually print, and let's print the pointer offset and the file offset inside our console. I will use f dot with apostrophe. You will see why I use f. It's because I can use string interpolation. So writing string like this and using variable with the bracket. These are in decimal. Let's show it in hexadecimal. And then put a dash and do text offset like this, x file offset, something like that. And maybe file offset instead. Okay. To now we can run and we will see all of our offset. You remember we had 2 pointers that actually looked at the same text. At some point, it might be useful to only store once the text and have a list of all the pointers to update, because maybe you want to update the text once and updates all the pointers. So later we might want to do something, and we also have another duplicate here. This will happen a lot. Sometimes you have a string that is repeated like 30 times. And now with that, we are able to read a pointer table, read the pointer offset and the file offset of each of our strings. And if we have the offset of the string, we can actually seek and go at the start of a string and do something to convert these bytes into Japanese text, and I'll then write it to some text file. That's what we will do in another session. For now, we know how to read and write a binary file. Maybe I also want to do some structure and put it more clean. So I also have another session to maybe create a couple of function and try to see how we can improve the structure of this. Thanks. Have a good day. Bye bye, everyone.